All right, generally on these, oops, rather than me just do the problems, I will ask questions and I will proceed when people reply to these questions. All right, so this is 14A. So first oxidized it and then added SOCl2. Okay. Maybe I'll use a green color today. Ah, green's nice. It's dark. All right, so we're gonna. Oh, okay. So this is we can try to do this. So you're saying we took this alcohol, we added something like Jones reagent, chromic acid. You got this acid and needed SOCl2 to make the acid chloride. Then I added azide and heat to get the product. So this is where this process may not be the best way to go. So if we do sodium azide and heat, this is the Curtius rearrangement. So let me draw out why this ends up being a bit of a trap. So if we draw out this acyl azide and we look at the mechanism of how this works, where we have this resonance structure, I'd like to put this negative charge on the oxygen. I think it's easier to see how things go. So we end up having, Layla's doing something else. So this can now go up, down. We get a 1-2 shift and kick out nitrogen. This will give you this product. So note that the isocyanate here has 4 carbons. This one only has 3 because one of the carbons became incorporated into the isocyanate. So actually the Curtius rearrangement would not be a very effective way to do this. So Layla suggested something a little different. Where after we got to this, after we got to the acid chloride, let me check a setting real quick. There we go. Cool. Got the settings fixed. So you said you added an HCNO. You added an. That's an interesting molecule. This is not a molecule that people readily use. There are some isocyanate salts you can have. Um, and I think if you imagine the substitution of this logic is correct in a way. The problem is we don't have a way to remove this type of carbonyl. In order to do this, we need to add, in principle, some sort of hydride or something like a Wolff-Kishner, and any nucleophile would likely react with this isocyanate competitively with this carbonyl as well. Yeah, there's not a way to go from a carbamate to isocyanate. So this is a carbamate. There's not a way to do this that there's some types of carbamates that are really bulky and you heat them up and they'll actually go to an isocyanate, but this isn't really covered in this class. I would say does anyone know an alternative way to make an isocyanate? Oh no, what I just did just highlighted why the path was not going to work. Yeah. So we've never really seen this reagent before. And if this were to do this substitution, it would probably have wrong reactivity. We couldn't get rid of this, or let's do it this way. Cannot remove, so you can't get to the product. Going with the courteous pathway, this is one of two ways we have to make isocyanates. This also doesn't get us to an isocyanate very well. So let's do some sort of phosgene reaction. Yeah, I like this. I like this plan. All right, so now our problem changes a little bit. I'm going to move this down a little bit so we can see it again. So now our question is, how do we go from an alcohol to an amine? So if we have, what reaction can we do to go from here eventually over to the NH2? Because we're suggesting that at the end, we can react this with one equivalent of phosgene and something like triethylamine base. And this will go and give the product. Yeah, so I am down with this. Cool. So we have, yeah, this is looking. There is a suggestion that I am feeling good about. Let me get rid of these things. So I'm going to couple a few of these steps together. Or maybe I can make a little. So we're going to use Jones oxidation. Then we can go up. We can take ammonia and DCC. This will make a primary amide. And then you're suggesting lithium aluminum hydride to reduce, and we'd have some sort of aqueous workup. This process is something that will be able to work. This one's looking pretty good. There's probably a slightly shorter way because in the last lecture we learned a few methods to make primary amines in particular. So you could also look at ways to do an azide reduction. So that would involve converting this alcohol to a bromide, displace with azide, and then reduce. So again, it's probably a similar number of steps. Alternatively, you could also consider doing a Gabriel synthesis. And this would also involve converting the alcohol to a bromide, displacing methylamide, and deprotecting to give you the primary amine. Cool. Does anyone else have any more questions on this? I think we're good. Yeah, so the courteous would give you one carbon too few. If we go directly from a primary amine, that'll leave you with the same number of carbons. All right, so now we need to go back. There's another question, that number 8. Let's go look at number 8. No, that's not what I want. So we're just looking for the major product of this reaction. Copy. Okay, cool. So you said you liked the answer B. So let's walk through it. How about suggest some of at least the initial products of each of these steps. I'll make sure that all the logic is correct. So if we have methylamine react with an anhydride, what will the product of this first step be? Yeah, so the nitrogen will end up attacking one of the carbonyls. So we know that anhydrides can be used to turn an amine into an amide. In this case, we also have this this other side, which will end up being our leaving group. So the leaving group will still be attached to the molecule. We had a darker green. So after, yeah, it makes an amide and a carboxylic acid on the other side after workup. Yeah, so there's an implied workup here with proton transfers that I think I did not write down. So now you can see where this is the leaving group, the acid doesn't do any more reactions. We don't have something like DCC to couple to it, so it'll just stay as a carboxylic acid. And then I think in your question, you said that excess LAH, that means we have plenty of it around. It'll be able to both reduce a carboxylic acid, which is true. Lithium aluminum hydride reduces secondary amides to secondary amines. And you see that in the product, we don't have any alcohols with neutral amines, and these are under acidic conditions. So sometimes if you add too much acid to a workup, you can in fact end up with protonated molecules. In this case, the amine would easily be protonated by excess acid. And yeah, I think your selection of B is not a bad idea. Most excellent. Got a new question. For 12A, I wasn't sure if the excess sodium borohydride would give hydrogens to all of the oxygens, or if you'd still be left with a double bonded oxygen making a carboxylic acid. Sodium borohydride cannot reduce carboxylic acids. So I would still encourage you to see if I can think at the very, no, not this one. I can go to this is from class today. So I think this is what we were discussing. And yeah, this will still hold true as well. So we pretty much have this problem where we've just connected these two together. So on one half of the molecule, it should get fully reduced, and the other half will still be there. So you should be thinking about a molecule that looks kind of like that. Because at the end of the reaction, we're going to end up with a carboxylate like this, or I can just draw it out. If it'd be useful, I can just draw this out again. Number 3, compare A and E. All right, let's take these one at a time. I hope the answers for 12A were clear enough. Going up to number 3. Okay, let's take a look at it. Okay, comparing between A and, oops, doesn't like that, between option A and E is the question. Sorry, I was looking at something else. So whenever we think about the reactivity of carbonyl compounds, um, there's the sort of energy diagram where we talked about ground state stability, where in all of the cases we have, let's say there's going to be some sort of leaving group. Well, let's call this a Y group because it could be a carbon or one of these heteroatoms. And we're talking about hydrolysis with sodium hydroxide, we'd end up having an O minus going and attacking this carbonyl. So this ends up being the hard step in the reaction. This is the one that's uphill in energy and the barrier that's difficult to overcome. So when we're looking at how fast things will react, we would want to be choosing the things that actually have the least ground state stabilization. So which ones end up having the carbonyl with it, effectively the least donating groups onto the carbonyl. So here and this is why we said something like an amide reacts more slowly than an ester, so the nitrogen lone pair can donate quite easily into the pi system. And in the terms of an energy diagram, we end up having energy barriers that for something like an amide versus an ester, their transition state energies and intermediates are actually pretty similar in height, but it's the initial energetic states that are different. So the amide has more resonance, it's more stabilized, so it's lower in energy. So if we look at a carbonate, does this have more resonance stabilization of the carbonyl, or does an ester have more resonance stabilization of the carbonyl? So the one that has the most donation is essentially the one that would have more resonance isomers. So in the case of a carbonate, we have two different oxygens that are donating charge into the carbonyl. So I'm getting to the edge of my page. Whereas with an ester, we only have one. So if this is more stabilized, it'll be slower to react. So this means that in the end, something like an ester will react faster than a carbonate. And so you can apply the same logic of why something like a urea will probably be slower to react than an amide as well. And the final part of this is, what would be the reactivity differences between A and B as they're both esters. And we kind of covered that today in class. Yeah, so when you have more donating groups for something that is electrophilic like a carbonyl, that'll lower its energy. So the carbonyl wants to take in electrons. The more electrons you can pump in from neighboring groups, the more it will lower its overall energy state. And that means that you'll have to break this resonance interaction to get to a tetrahedral intermediate. So notice in this tetrahedral intermediate, we no longer have this resonance interaction. So this is something that you're going to have to, the nucleophile will have to overcome. So with a carbonate, we have two different resonance donors that you're removing the interaction of, whereas in an ester, there's just one. Okay, cool. People are good on that. I will go to the next one. We had a series of questions. We look at number 10. Think maybe E, but I'm a little unsure about the nitrogen on the positive charge. I need better posture. Stand up straight. Oh, this is a great problem. So this is covered in lecture 26 a bit, or at least that's where we talk about alkylation reactions of amines and alkyl halides. So we got E as an answer. More than one of these is expected. But I'm a little uncertain if nitrogen would take the positive charge. So you're saying you're concerned about D being an answer, or so I would comment that you can have a reaction between a tertiary amine. If you had something like triethylamine and an alkyl iodide, this would have no problem going to a positively charged nitrogen with this counterion. These are stable. They're called quaternary ammonium salts. Oh, you were wondering which compounds will form? Wouldn't only D form? Isn't it so reactive it'd go all the way till the end? Yeah. So in this case, we have 4 equivalents of the iodide versus only 1 of the amine. And we have potassium carbonate. This acts as a base. So it'll always be there to take protons away. So during the reaction, you will go sequentially through formation of B, C, but at the end, since we have more than enough alkyl iodides to fully react all of the amine we have, each one of these amines will be able to react 3 times and go all the way forward. The times that you end up getting mixtures where you would expect more than one product is if we had a reaction between, say, this and 1 equivalent of ethyl iodide, or even 2 equivalents of ethyl iodide. This is when you'll start to see mixtures of secondary and tertiary amines and quaternary amines, and potentially having some starting material left behind. If you have a decent excess of the alkylating agent, those amines can continue to react over and over again, and it can push it all the way forward. The issue is usually more of a statistical one, where some of these intermediate products like B and C can still react again when maybe you don't want them to. Exactly. Since we have enough of the ethyl iodides, it will go all the way forward, and it can't alkylate any more than D. So there is a stopping point to those reactions. So it comes down to so it's kind of like how nitrogen is a good base. So protonating a tertiary amine actually is pretty easy to do. Like if you mix a carboxylic acid with a tertiary amine, it'll get protonated. And let's say we had a different reaction, only now we're going to add in, even HCl, for instance. Going to oops, I didn't mean to draw that last one. Going to this salt will actually be downhill because the HCl brought a lot of energy with it. In this case, we have this alkyl iodide. So this, in some ways, you can make some parallels that alkyl iodides also are quite reactive. Making a carbon-nitrogen bond ends up being a stronger process. Oops, I don't know why I had a bromide here. That should be an iodide. This ends up being an overall more stable configuration. And this still allows it to go down. So tertiary amines actually really have no problem going to a positively charged state. Kinetically, the backwards reaction is also kind of slow, but this has to do with some other different factors. Okay, let me scroll up and see if I can add to any of these questions about this. This may be a silly question. How many equivalents do we need to start considering the reagent as excess? So in order to do this, you would want to consider how many times something could react. So in principle, if you're using, in this example, this NH3, oops, no. Sorry, it's been a long day. And we think about the final product where it no longer can react and make any more bonds is with 3 of these ethyl groups. We would need to have at least 3 equivalents of ethyl iodide to make this product essentially perfect, completely. This is assuming no other side reactions and stuff, but this is a pretty reasonable assumption. For, I said 4 equivalents just so that you had even more. Adding extra equivalents will just make reactions go faster. And just to make sure that people weren't trying to maybe overthink it and consider maybe there's a side reaction, maybe something else could go wrong. And we did not agree that more than one product could form. And that's because we have a very large excess of the alkyl halide. So all the intermediates can continue to react. So since we would still have ethyl iodide around, A could go to B, all of the molecules that form B can go to C, and all of the C's will be able to go to D. So 3 would be the minimum number of equivalents to get you all the way forward. 4 would leave you with still 1 equivalent of ethyl iodide after the reaction's done. Cool. Going back to 12A. Oh, this guy. Okay, I'll just copy and paste this guy. And then I'll go back up the list for whatever we have time for. So this is our question. Actually, I'm going to crop this a little bit. We don't need this whole thing. Oops. No, delete. How do I use the crop function? Oh, there we go. So at the beginning of class, so if you only had 2 equivalents, would you only be able to get to C? If we had 2 equivalents, then we would end up making, sorry, I'm going to go back to 10 real quick since we had another question on this. If we only had 2 equivalents of ethyl iodide, we get in a slightly different scenario. I wrote a lot of things everywhere. I'm just going to erase some of this stuff. If we only had 2 equivalents, as things react, we would actually end up probably making some D along the way, and we'd probably end up with some B along the way too. It's because as this is then a case for 2 equivalents. So 1 equivalent would react, and so we'd have some B in solution. And then along the way, some of that B can react to go to C. Before all the molecules get to C though, we're going to have C competing with some molecules of B and maybe even A, and some of that will end up reacting further to go to D. So if we only had two equivalents, then we'd end up getting more than one of these products. So this is where we can't really control just adding in one or two. We can go all the way, but anytime you try to target one of the intermediate alkylations, you will get mixtures. Okay, so now I'm going to go back to, I think, 12A. So in class, at the beginning, we mentioned that we have an anhydride. These can, in fact. Oh, I just muted someone. Anhydrides can react with sodium borohydride, and they will react to give, after workup, an alcohol and a carboxylic acid. This is because after the first addition, we make a tetrahedral intermediate. We have our good leaving group. The tetrahedral intermediate collapses. This gives us an aldehyde plus a carboxylate salt. So this carboxylate salt cannot be reduced any further, and it kind of stops here. This aldehyde, though, it can be reduced more by sodium borohydride. So after workup, one of the carbonyl groups gets turned into an alcohol, and the other carbonyl group essentially all is a leaving group, and it goes to a carboxylic acid. So in this case, we have the same scenario, only now we kind of have our leaving group once again attached to the side that gets reduced. So either of them could react initially to make the leaving group on the other side. This will attack. This can go up. We make our tetrahedral intermediate that has a good carboxylate leaving group. We get to an intermediate aldehyde, carboxylate, and this can continue to reduce again. Does this clarify 12A for everyone? It depends on how strong your workup conditions are. You'd be able to control this. So if we did this again, and after workup we get this, depending on how strong of acid it is, you potentially could see some of this. So if this were too high of concentration, even, then you might even do a Fischer esterification to give a lactone. But this is not the answer I was expecting. I posted on Piazza or somewhere, I think someone asked, if you were to leave this in a charged form on the problem set, I would be A-okay with that. If you want to do an assumed workup, I am also okay with this too. So if you put in something like this, I wouldn't have a problem. In my mind, this is again where I was just making something and forgetting to write all my workups. In my mind, I always assume there's a workup when I see sodium borohydride, so I would have written the alcohol carboxylic acid form. If you would have added concentrated HCl to work this up instead of dilute HCl, then you might get a lactone as well. But I wouldn't put that as an answer. Okay, 14B. Okay, I'm going to go back up because we had questions earlier. I want to make sure that I'm going somewhat in order. Oh, great. Wait, there was a question about number 4. Did we do 4? I'm going to go to the problem set either way and see. Which of these is the least electrophilic? And then we'll get to this, the DCC question again. Or not again, the first time. Just trying to stay in order. First come, first serve. Okay, I chose A, but it won't be E because of, we're looking for the one that is the least electrophilic, but it won't be E because of resonance stabilization in the O anion of the ester. So an ester actually, so let's go through this. So an ester would actually be less reactive or less electrophilic than a carbonyl compound. And that's because of the resonance structure that occurs. We can think about how sodium borohydride can reduce this, no problem, but sodium borohydride cannot reduce esters. That's because it's less electrophilic. I chose E because acetone would be an electrophile and a nucleophile. So acetone's rarely a nucleophile. Sometimes it can be a base, but usually you need really strong acid. Why would it not be C? C is also a pretty good consideration. I was at first just comparing A and E because these are the two things that were brought up. So I think most people can see that B and D, they're positively charged. We can probably cross those out immediately because they're going to be quite electrophilic. C and E are actually maybe the most difficult to compare, and I can see how there could be problems if you're wondering about what is the effect of this resonance energy versus the change in heteroatom. But something we want to consider is if we have a nucleophile attack, let's look at the products. So similar to how we were analyzing acidity and basicity in class today, we can look at the product stability and get some sort of estimation of maybe how hard the reaction is. So let's just say we have a generic nucleophile N that's negatively charged. No. Go. So we could maybe consider attacking each one of these. We know that the difficult part of additions to carbonyls, where they act as electrophiles, is the formation of the tetrahedral intermediate. And so we could also consider which one of these would be higher in energy or lower in energy. Which one, let's say which one is more stable. Would an O minus be more stable or an N minus be more stable? Yeah, so the O minus is more stable than the N minus. That means that probably attacking an ester is going to be easier, which means it's probably more electrophilic. There is this, I guess, gray area of what is the contribution of this resonance interaction, because we do have the other oxygen donating in. I would probably make the argument that these N minus species, we only see them as like mega super bases that can deprotonate benzenes. So this is pretty crazy high in energy. And this is, if we consider just the pKa of an amine versus an alcohol, these are 20 orders of magnitude difference. So in order to generate a very high energy intermediate, That means that this probably isn't very electrophilic and would be less electrophilic than an ester. Note that whenever we do reactions on things like an imine, like in the last section we learned reductive amination, the reductions always go through an activated form, where we actually have a protonated iminium that gets attacked instead of the neutral imine bond itself. Hope that clarifies that question. I'm going to go back up. I got to scroll up a lot. We're going to talk about 14b now. Where we have a question mark here. So we have a reagent, this lithium triterbutoxyhydride. The question is, I wasn't sure about the best approach to this problem. Wasn't sure if there's a downside. Am I on the right one, 14b? I think I did 12b. I did just do 12b. 14b. Okay, sorry. Let me go back to this. I'm sorry for misreading a question. So I used DCC in the reaction. Would that be okay? I wasn't quite sure about the best approach to this problem. I wasn't sure if there was a downside for using DCC for this synthesis. Someone's asking about a GMAP reaction, so let me go back and think I can hit all of these at once. Oh, I can answer this since this is where I saw 12b. Just to quickly answer this one, there was a question on why is there a workup? Technically, you don't need to neutralize the carbonyl. The aluminum salts would be worked up with the H3O+. So yeah, for getting to the aldehyde, you don't necessarily need a workup in that reaction. Okay, okay. Now I think I am back. We can talk about this. So I think DCC is a great way to handle this problem. So I said all the carbon atoms must come from the starting material. So that means is these carbons will end up right here, and these carbons will end up over here. That means we're going to have some oxidation state changes. We have this alcohol coming in. And I do like the idea of doing a retrosynthetic disconnection, where we're going to go back to an alcohol and a carboxylic acid. This is the way I would join these together, and I would use DCC to do this. But remember, if you have an alcohol and an acid with DCC, we need to add in DMAP. So DMAP is used to further activate the activated ester along the way to get the reaction to take place, just like, sorry, if you were to use an anhydride. Okay, I'm going to go back up. I think there's something else I missed. How does the mechanism work? Where does DMAP come into the mechanism for 7C? That might be able to answer this using that question we just had. Yeah, so this will be able to answer. Let me use the other one as an example for what DMAP's doing here. Um, so whenever you have this molecule react with DCC, this is our cyclohexyl carbodiimide. The first intermediate you make is actually looks like this, where the carboxylic acid kind of adds across the carbodiimide. So this alone is not quite reactive enough to directly, this isn't reactive enough to take on the alcohol and have it attack this carbonyl. So this is similar to when we had an anhydride and we wanted to get it to react with an alcohol. This reaction was very slow. So we added in dimethylaminopyridine. Note that this is a very nucleophilic amine, and it will be able to attack and make a tetrahedral intermediate that then collapses. So I'm going to draw just kind of skip 2 steps. We end up with these very reactive acyl pyridiniums, where you can draw it in this form, or you can have this resonance isomerization with that go all the way down. So we have stabilization from this nitrogen in the back. And these are very reactive. And this is what an alcohol will end up attacking. So DMAP is something that comes into the mechanism. It is essentially is more nucleophilic than an alcohol and leads to an intermediate that is very reactive, but then it also ends up being a very good leaving group, so it's regenerated. So you only need a small amount of it. So you could write a catalytic amount of DMAP. In this case, DMAP would be attacking this group in the same way and eventually having this as the leaving group. So this kind of, sort of, if you cross your eyes, looks similar to an anhydride. Note they have some similarities in bonding. And so this will lead to essentially the exact same acyl pyridinium intermediate. You can use sulfuric acid, the Fischer esterification. And the Fischer esterification, you would need to have something to really drive the reaction forward. So if you did it with like a Dean-Stark trap or something like that, that's fine. And in this class, it works. DCC DMAP is probably what someone would do in a laboratory. Fischer esterifications are really useful if you want to make something like a methyl ester, because you can use methanol as the solvent, and that the statistics will push it forward. In this case, you would probably want to have several equivalents of benzyl alcohol, and that might become a little harder to remove because it's not terribly volatile. Staying on 14b, would you be able to start off using KMNO4 even though there's a double bond? So KMNO4 will actually cleave the double bond. Is that what you're trying to do, is to break the double bond in half? Then that is a good thing to try to do. So there's the things where you can do KMNO4, and you end up with 2 carboxylic acids. This will get you going in the right direction. So this already gives us one component that we need in the reaction. Now you just need to figure out how to do that. So the problem with the MCPBA route, epoxidized, then a base. So if you try to add MCPBA, you'll go through the epoxide. I don't know if you guys learned periodate cleavages, but I would definitely be trying to use some sort of reaction that will break this bond in half. So you could try to do something like ozonolysis or something like the potassium permanganate reaction. The hydroboration process actually gives you into, yeah, so at Madison, I think you are good to go. The hydroboration process is tempting, Um, so this is where we have, make sure I have the starting material. There are 2 carbons there. We have 3 carbons here. So if you did hydroboration followed by oxidation, this will selectively put a hydrogen here and an oxygen here. So that's not bad. We could do something like PCC to oxidize it to this ketone. And you're saying MCPBA to do the Baeyer-Villiger oxidation. The problem here is that both of the carbons attached to the ketone, they both can migrate. So you would have probably similar chances of this bond migrating as this bond migrating, so you'd get mixtures of products. If you go for one of the reactions where you cut this double bond in half, then you can control the oxidation states of either side independently, and then you'd have more selectivity in making that ester bond. Hold on 1 second. All right, sorry, I am back. Um, wouldn't the benzene help stabilize? It could, because that will be a little bit better at stabilizing positive charge. The selectivities on those actually aren't that great for probably those competing interactions. That's a reasonable rationale, though, because benzylic carbocations are more stabilized than, say, a primary carbocation. I'm just saying that this would still be risky because um, the selectivity still won't be very exclusive, whereas in these other alternatives, you will definitely. If we chose this route on the exam, well, this is not on the exam. I would have to decide then. So part of the challenge is kind of figuring out like what is the rationale for why someone was doing this. If you're using all reactions from old topics to solve a problem when we're learning about esterification reactions, I would probably be safe to assume that you would want to be using the reactions from that section to solve it, especially if it ends up being a potentially risky maneuver. I would say that problems on this exam generally will be, at least the meat of the problems will be will be testing the topics within the exam. I mean, there are exceptions. Sometimes I come up with a problem where I want people to use a certain reaction to come up with other ideas. Usually they're not punished. Usually good syntheses will be fairly graded. Um, but even for me, you might get the right product as the major one, but I think you're still going to have some of the other side product as well, probably in quite a bit. All right, let me go up and see where I am. Someone's asking about 12D. I think I'm on in 13. I think it's Anastasia's question next. 13. Do we have to show steps in the workup to replace the primary amide with a hydroxyl? We did not go over that. If you check the Yatsa, this is, I believe, drawn out in the book, and it follows a lot of the same ideas that we have for. Um, so once we go from here to here, we'll use the same sort of rationale for, say, hydrolysis of an ester. We're going to start with protonating this carbonyl. We're going to have a neutral water attack this tetrahedral intermediate. I'm going to draw 2 steps. After you get to this intermediate, we're going to end up having proton transfers to turn the amine into a good leaving group, and then this will be able to depart. So this is an abbreviated version. I think on Piazza I referenced the part of the section of the book where this is. I might have time for one more. I do have another phone call at 6. "12D. I think that is this one. All right, 12D. I can maybe do this one quickly. With this, I use 2 steps: sodium cyanide and then LAH. That will add another carbon. I would go look at lecture 26, or even I think the reaction overview sheet. Overview sheet. It shows all the different ways to make primary amines from either primary amides. And there's 2 reactions that we learned in lecture 26 that would be very applicable for doing this interconversion. So for the person who referenced using sodium amide, so that's actually, so I think if you meant this type of nucleophile, turns out this is a really good base, and you're going to end up just eliminating that bromide. If you try to react something with just NH3 as ammonia, you're going to end up with the alkylation problem, where the product will start to compete and react with the other one. This will require a 2-step procedure to do selectively. Seven C. Yeah, exactly. Azide in DMSO will give you to the azide, but then you'll need to reduce the azide. Oh, azide. Yeah, azide's all good. Azide, and then you need to reduce the azide, and we can do that with lithium aluminum hydride or platinum oxide and hydrogen gas. I want to see if I can answer 7C quickly. Oh. I don't probably have time to go over 7C right now because this involves talking about a number of different scenarios. But there is always tomorrow night. All right, I'll be back here, same place, same time tomorrow night. Here to hopefully answer as many questions as I can. Well, you guys will be seeing me later. I guess I won't be seeing you as much. Hope everyone has a good evening.